Do you have a fan makes a little too much noise? Maybe it sits on your dresser and click, click, clicks away, or maybe it hangs over your head and it drives you crazy. Maybe you can't sleep at night. Well, I'm going to show you a simple way to balance that fan. All you're going to need is some tape, some weights, some way to measure the vibration, and some way to draw circles. So let's get started. As a first step, you're going to want to put your fan onto a surface that actually displaces a little bit. Here I'm put on a box, has a little bit of bounce to it. Let's go ahead, shut the fan off, remove the front, and using a Sharpie marker, something to label the blades. Here we got 3 blades, so I'm going to label them 1, 2, 3. Now we have to get a tool to measure the vibrations. I'm using an app that takes advantage of the accelerometers in my cell phone called Gauges. I had to pay $3 to unlock the Pro feature that allows me to export the data to the computer. We'll get a look at that in a second. Now that we're ready to start taking measurements, go ahead and put the cell phone down, and we're going to record the baseline vibrations. In other words, how bad the vibrations are before we start to make corrections. Here I am recording a few seconds of data. I'm going to shut the fan off, and now we have to prepare a trial mass. Using a small piece of a paper clip, I tried a penny first, and it was way too heavy, caused too much vibration. So the trial mass, I'm going to be sticking it onto the blade, starting with blade number 1 here, sticking it near the edge of the rim. You want to do the same mass at the same relative location on each blade. Wait for it to come up to speed, and we're going to be recording a few seconds of data with mass taped at the first position. Then let that slow down, and we'll replace the mass. We'll move the mass to the same relative position on blade number 2. Lather, rinse, repeat, and we're going to, at the end of it, we're going to have a baseline measurement, and we're going to have 3 trial mass measurements where we've moved the trial mass to the 3 different blades. Okay, so this is what the data file looks like. It has a lot more information than you'll need for the purpose of balancing your fan, but that's fine. In my case, the app recorded a separate column of data for each of the 3 axes of motion, X, Y, and Z. Because I had the phone laying on its back, the fan vibrations induced a Z direction acceleration in the phone. So that's the column of data that we're going to focus on. Your phone or your app might record things differently, but if you've followed me this far, you will figure it out. Here's a plot of the Z acceleration for the baseline case. You can see maybe 50 cycles that it recorded over a few seconds. The app that I use puts out acceleration in terms of gravity units, G. So that's why it's centered around -1. You'll notice that this data also exhibits a subharmonic. Okay, in addition to these individual cycles here, 1, 2, 3, 4, 5, that's the rotation of the fan, but there's also a lower frequency subharmonic you can see. So this means you've got to be careful about how you extract the vibration amplitude from the data. If you just grabbed, say, the high and the low from the file and said, okay, the peak vibration here, and well, I guess it might be this one, and the lowest vibration here, that if you tried to use that as the amplitude of the vibration, that's not going to be accurate. You really want the fundamental frequency, the frequency due to rotation, which is this higher frequency amplitudes. Engineers have tools for very accurately extracting out the individual frequency amplitudes for all the frequencies in a given waveform, but because I'm trying to make this method as accessible to everybody who might not have access to these tools, I suggest you just zoom in on a single cycle of data to get the fundamental peak to valley amplitude. So let's look at that here. If we zoom in on a few cycles of data, this is actually, see, now we're down into the couple of milliseconds. This is the amplitude we want. This peak to this valley, that's what we want. And for the baseline case, I'm measuring this to be about 0.165 G units. Okay, so 0.165 G units, I've recorded that as the baseline, and in the same fashion I went into the data for trials 1, 2, and 3, and I recorded their amplitudes as well, and I've got them all listed here. Now's the fun part where we actually use the graphical method to find the solution mass and location that will put the fan back into good balance. First thing you want to do is to draw a circle. I'm going to multiply everything here by 10 just in case you wanted to do it. You could do that. There's nothing wrong with multiplying everything by 10. Just so you could use inches. You could do this with a protractor, okay? I guess you could do it a couple different methods. I like to do it on a computer. If I had a protractor, that would probably be just as easy. But you draw a circle, you get a ruler, whatever, you measure out your 1.65 radius, and you draw a circle. So this is our baseline circle, okay? That's 1.65 units in radius. Then, because we have a 3-blade fan, you're going to have your 3 blades represented here. And what we're going to do is we're going to draw circles centered at these intersection points. You'll see. The first one is the radius. Trial 1, we put that little piece of paper clip on the first blade, okay? And the vibration jumped up from 0.165 to 0.221. So again, I multiplied everything by 10. So I went and I drew a radius of 2.21. I drew it here, centered here. So this is what it would look like if you had a compass. It would look like that. Likewise, I did the same thing with trial number 2. Then we do trial 3, and boom. Now what you really want to find is the intersection of all 3 spots. And it looks like the intersection will be right close to here. I'm going to draw a little X there. It's at the intersection of these 3 circles. The position of this X shows us 2 things. First, how much mass to add, and second, where to put it. We need to do a little simple geometry to solve for the amount of mass that's needed to eliminate the imbalance. Simply put, the solution mass is equal to the baseline radius, remember that, divided by the radius to the intersection of all the circles where the X is, times the trial mass. And you can see the baseline radius is about 3 times as big as the trial mass, so the solution mass is equal to 3 times the trial mass. Okay, so that answered the question how much mass to add. Now we have to answer the question of where do we put the mass, which blades do we put the solution mass on. Well, let's forget our friend X for a second here, and let's think about it. What if X was here, over on the position of blade number 2? If it were here, then we would put all the mass on blade number 2. And likewise, if the mass were over here, or here, or anywhere close, even maybe here or here, we would put all the mass on blade number 3. Well, that would have been nice, but our X was here, in between blade 2 and 3. So what do we do? Where do we put the mass? We can't put it out in outer space in between blades 2 and 3. Well, what we're going to do is we're going to trick the fan. We're going to add a little bit to each blade, and we're going to trick the fan into thinking that we've put the right mass in the right spot. Let's pretend for a minute that our mass was right in the center between the 2 blades, right? 3 times the trial mass. Believe it or not, you can get there by putting 3 weights along blade number 2 and 3 weights along blade number 3. You'll get to the same spot. You'll essentially trick the fan into believing that you've added 3 weights right in between. Full disclosure, I re-ran this experiment and ended up with a position that was shifted a little more towards blade number 2, as you can see here. You end up with a position that is a little more interesting to calculate. You can see here, I ended up putting 4 masses on blade number 2 and 2 masses on blade number 3. And because I'm a little bit of a geek, I did write a script in an open source program called Octave. The script reads in all the files and plots things out. And my analysis shows right here, this is the baseline vibration. Trial 1, 2, 3, and then here's the, after adding the solution mass, so the vibrations are down pretty low. This is where it started, and this is where about a 75% reduction. Well, there we go. Enjoy. I hope the if you folks get something useful out of this. Sleep easy with a nice quiet fan.